Welcome to the fourth lecture from chapter number 7. The last lecture we studied CMOS not, some basics of CMOS not, the VTC and the expression to derive VM, the middle voltage, and we also studied about the symmetric knot where VM is exactly equal to VDD by 2, and we discussed about the settings that when beta n is equal to beta p and Vtn is equal to Vtp, we get a symmetrical CMOS knot. In this lecture we are going to study an example where we are given the process transconductance values kappa n, kappa p, the threshold values Vtn and Vtp and Vtd, and we are asked to calculate the value of, in fact the problem has two parts. In the first part, part A, we are asked to calculate Vm given that beta n is beta p. So that's simple. Vtn is already equal to Vtp and we are given beta n to be equal to Vtp. Of course, we are gonna reach up to a value equal to Vdd by 2. We know that Vm is Vdd minus Vtp plus the square root of beta n over beta p times Vtn over 1 plus square root of beta n over beta p. Right, so we have Vtp and Vtn, the values are equal, the values are given to be equal. So what we are going to put is Vdd, so 3 minus 0.7 plus this ratio is 1 because beta n is given to be equal to Vtp plus 0.07 over 1 plus 1, so we get 3 by 2, 3 over 2 is 1.5 volts. So Vm is very simple. Next part is that now we insist that we want aspect ratio of, don't rush to the next part. If we have Vm, we also have to find the aspect ratio of n and aspect ratio of p. So, and then we'll be going to part B. Let's find the aspect ratio of p and aspect ratio of n in part 1 when beta n is equal to beta p. If beta n and beta p are 1, this means beta n over beta p is equal to a 1. So why have I have written this 1 very far away from this ratio because we have to write, because I want to write beta n equal to kappa n aspect ratio of n, and beta p is kappa p times aspect ratio of p. So this ratio is 1. Right, so we know the value of kappa n is 140, the value of kappa p is 60. So this is 140 over 60 is equal to 1. So this leads us to, if we take this here, this becomes 60 times aspect ratio of p. This is actually the size, so if we can write it like this, and aspect ratio of p can be written as, taking the 60 on the other side, this becomes 140 over 60. It is 2.33 times aspect ratio of n. So the aspect ratio is actually the size. We'll study aspect ratio in more detail in the upcoming lectures. Aspect ratio means the size. So this tells us that if we want to implement a symmetrical knot in this setting, we have to draw for a symmetrical knot of this, for a symmetrical knot given these values, we need to draw PMOS of size 2.33 times larger than NMOS. So if your PMOS is 2.33 times larger than your NMOS, you will be experiencing a symmetrical CMOS not in this setting for this example. So that's great. So aspect ratio of P is larger than aspect ratio of N if you want to draw a symmetrical knot. Let's move to the second part B, where we insist that instead of beta N to be equal to beta P, now we insist that we want the aspect ratios to be, or the sizes to be, the same. We want to have both PMOS and NMOS of the same size. We want to have both PMOS and NMOS of the same size. And what should be the VM then? Of course, that won't be a symmetrical knot. That would not be a symmetrical knot. Because for a symmetrical knot in this setting, for these given values, we have to draw PMOS 2.33 times larger than NMOS. So if we insist on having PMOS the same size as NMOS, of course that won't be a symmetrical knot. But what would that be, and what would be the numerical value of VM? That's straight away VDD minus VTP plus square root of beta N over beta P times Vn over 1 plus beta N over beta P. Right. So, and we know that beta N is kappa N aspect ratio of N, beta P is kappa P aspect ratio of P. So let's plug these values here. Beta N over beta P. I'm going to write kappa N aspect ratio of N over kappa P aspect ratio of P, and of course the square root, and the same thing here, kappa N aspect ratio of N over kappa P aspect ratio of P, the size. Right, so since the sizes are equal, they cancel each other, and now we are able to put the values. Instead of kappa N, we put 140, kappa P is 60, kappa N is 140, kappa P is 60, VTN is 0.7, VTP is 0.7, VTT is 3. That's all. Now we are done. And this VM, if you calculate, you can calculate yourself, it comes out to be 1.33 volts. So it's not symmetric, it's not 1.5, it's not equal to VDD by 2. Therefore, it is not symmetric. So it isn't symmetric, isn't a symmetrical knot. So as for a symmetrical knot, we have to put beta P is equal to beta N, and beta N should be equal to beta P. And for any other values, it won't be a symmetrical knot, and you'll get a VM that is close to VDD by 2, but won't be exactly equal to VDD by 2. That's all for the DC analysis of CMOS knot. In the next lecture, we will start studying about the transient analysis of CMOS again. CMOS knot. Thank you.